the previous module, we talked about thermal comfort and the physiological processes behind thermal comfort. This module talks about thermal adaptation, the concept of thermal adaptation, and what is the idea behind this adaptive comfort model and the studies. Primarily, this would talk about the physiological dimension of psychological as well as physiological, it is psychophysiological dimension of thermal comfort. Then we will talk about thermal adaptation and what are the factors behind thermal adaptation. We will talk about how do we assess or measure thermal adaptation, lot of field studies are being conducted. So, we will take a look at how to go about these field studies, and then we will take a look at a few adaptive comfort models which may be relevant to design of buildings. The psychological dimension of thermal comfort. In the last module, we looked at comfort as a perception or an expression of satisfaction to the thermal environment around a person. But today in this session, we would look at comfort as a negotiable socio-cultural construct. What happens? Comfort is not just physiological, it is not just the thermal regulation, but how we perceive and react to the thermal environment. We are under constant interaction with the environment, we will look at it in more detail, but with this practice comfort becomes a negotiable socio-cultural phenomena. Which society we belong to, what culture we grew up in, this determines what is our expectation to a particular thermal environment, what do we need, what do we want, and how do we perceive a given thermal environment. If we look at the building design, vernacular building styles were more responsive, they were meant to be climate responsive, but due to space constraint, demand for spaces, the type of construction has underwent a wide transformation. That is why we are re-looking at how comfort can be assessed and how to design buildings for comfort itself. In the last modules, what we saw is a person's body physiologically regulates itself to the thermal environment. Say for example, let us start in this chart, let us start from this point, the present heat cold loads on a body. What happens? There is a physiological thermoregulation process which the body undergoes. Because of this, we start perceiving or experiencing a particular environment. Here there are three different things. First is a thermal effect, how the environment affects you, then we start talking about comfort, discomfort, and then we start sensing the thermal environment. So, this is the first part of it. Now, what do we do? What else connects to thermal comfort? There is a huge set of parameters which is connecting to thermal comfort. The first thing is the past thermal environment. Say for example, you are moving from a place like Srinagar to work in Delhi. During summer, you cannot stand it for the first year, for the second year, and eventually third, fourth year you get used to it. So, it is a long term thermal experience which is needed to get adjusted to a place. Similarly, you move from a hotter zone to a colder area, you need a quite a longer duration to adapt, this is long term, but then suddenly it rains in summer. The first day you are happy, second day it is raining, but third day it starts getting sunny again. It is a short term thermal disturbance. So, your body gets acclimatized to the heat, suddenly it rains, so there is a thermal readjustment, and then when you get sun again, you cannot tolerate it for the first day, second day, but in 2 to 3 days time you get used to it again. This is a short term adjustment. So, this is the short and long term past thermal environment. Then comes the climocultural practices and norms. There are certain cultural practices, it starts from the dressing code, it starts from our food habits. People living especially in composite climatic regions have a specific way of food habits during summer, during winter, during monsoon times. This is quite well adapted food practices, climocultural practices and norms. Then you have environmental adjustments which a person does, it can be active or passive, it leads to behavioral and technological adjustments. So, these things totally comes back. First you had the thermal effect, comfort, discomfort and sensation. Now we get another component called thermal expectation. These thermal history as well as your climocultural practices and norms together lead to something called thermal expectation. I am expecting something in this summer in this particular city. So, this leads to an expectation which has a lateral impact on the perceived comfort, discomfort as well as the thermal sensation. This together leads to something, the term called satisfaction. I may be comfortable but I may not be satisfied. There is a small difference between having a sense of comfort, having perception of comfort, and expressing a thermal satisfaction. We will look at it little more in detail for better clarity. Then this also affects the thermal preference. Say for example, like the earlier example I said, I am moving from Srinagar all the way to Delhi to work. My thermal preference because of these practices is something, but what I sense and what I experience as comfort is different. Because of this, my satisfaction with the thermal environment is varying. Because of these things, I go for behavioral or technological adjustments. Behavioral can be in terms of changing your dress, changing your activity pattern, doing or not doing certain activities, changing food habits. If these things do not permit or you are not willing to do these things, you go in for technological adjustment. Simple thing, you buy an air conditioner, you condition your room 1, 2 numbers of units, technological adjustment happens, which again comes back and affects your environmental adjustments. So from a naturally ventilated or a free running environment, you are moving towards a technologically controlled, mechanical controlled environment. This again determines your heat or cold loads on the body. So this total thing becomes a loop. What are the factors primarily influencing this? I have indicated specific clusters with color codes. For example, the first thing is seasonal variation from summer to winter to monsoon to spring to autumn. There is a considerable variation between the season which significantly affects thermal adaptation. Number 2 is a microclimate. Moving from suburban area or a rural area to the city, you have a significantly distinct microclimate. I am going to show you some specific evidence or documentation which we made in this regard. These are environmental variables. Then the next set is personal variables where age, gender and state of health. For example, during field studies we found a considerable difference in adaptation, thermal adaptation with respect to age as well as gender. For example, older peoples did not complain much about heat discomfort during summer, but they had more comforts, more complaints about cold discomfort during winter. Similarly, when we talk about age, another critical example which came up was the younger set of people less than 20 for example had a preference for lower temperature compared to people who were say above 50 years of age, mid age and old age people. State of health has a clear impact. We will talk about this little in a little while. Then the nature of work you do, both the metabolic activity which determines the MET value which we talked about, it depends on how much metabolic activity or heat production your body is undergoing. On the other side, it also depends on what kind of position and place you are stuck to. For example, if you are a IT professional, you are a student sitting in a classroom, you are bound to your seat, you do not keep moving around, you do not have a flexibility to switch on, switch off your air conditioner or your fan. It is not your personalized control. Whereas you have a single cabin, you are sitting in this cabin, then you have more flexibility over the light, fan, opening or closing the window, set temperature, lot of controls are available. So the nature of work you do, whether the workplace is air conditioned or naturally ventilated, has a lot of impact on thermal adaptation. Apart from this, you have the availability of thermal adaptive opportunities, whether I have access to controlling the fan speed, whether I have access to controlling the air conditioning set point temperature, whether I have operable windows which will facilitate better ventilation. So presence or absence of adaptive opportunities, this is where the role of designers come into picture. For example, you design a building, you have an office space, whether you are taking care of providing an adaptive opportunity so that this person sitting in this cabin is going to use that opportunity sometime or the other to make himself comfortable for a few more hours rather than opting for a opting to switch on an air conditioning system. Then we talked about these two phenomena. These are like more psychological, short term thermal experience, like a sudden change of weather during a particular season, say a typical sunny days in a rainy season, monsoon season, or a few rainy days in the summer season changes your thermal experience. Your body gets needs a few more days to acclimatize back to the summer condition after the rain. Long term thermal history, it depends on where you grew up, what you know about a particular season. Your summers may not be as harsh as where you grew up, would not be as, probably may not be as harsh as what you experience in the place where you work or where you study. So there is a lot of difference, or it takes a lot of time for you, at least a few years, to get to this acclimatization. So this is short term and long term. This is not an exhaustive list, but these are some major parameters which influence the thermal adaptation process. In short, I would like to present this as a graphic for your understanding, an infographic for your understanding. This is more or less covering the theme of what we have been discussing so far, and few other modules that we will discuss after this as well. Let us start this from here. There are three main components. The first is the environment, say outdoor environment. This is a major component. The thermal severity of this particular environment affects comfort, influences comfort. Then you have occupants, people who are perceiving comfort or perceiving the environment. So about the people by themselves, like we discussed, age, gender, body mass index, lot of things on their own, their physique affects the perception of comfort. Then number 3 comes the building. How we design a building, actually this is where we are going through. We started the module somewhere from environment, now we are moving towards comfort and occupant. Next we will be talking more about building, then we will go to comfort and energy efficiency in buildings. This is where we are moving around. The first is environment, how the environment itself is severe. We talked about climate. Now we are talking about occupant, the physiological as well as physio-psychological part of occupant comfort. The next would come the building, how building impacts the comfort. But now what we need to understand, these three entities are not acting by themselves independently. They are partly independent, partly they are dependent on each other. Environment is an independent variable, but then occupant interacts with environment. This particular interaction, how he perceives the environment, we talk about thermal comfort, thermal perception, then we talk about thermal history, thermal adaptation. So his experience of the environment determines adaptive thermal comfort. So how the environment by itself is, how his body reacts, what is the thermoregulatory phenomena, plus how in long term or short term he adapts to the thermal environment. So this interaction builds us the adaptive comfort criteria. Next part is how building interacts with environment. We will look at this interaction more in detail, but to look at it short, we talk about climate responsive design. We did look at some vernacular principles which were being adapted to be more climate responsive. So there is a thermal severity in the environment for most of the climates. Then we design our buildings, and this building starts reacting with the environment. This is more or less a deterministic way of reaction, or eventually it is a cyclic phenomena, it keeps happening. Unlike this interaction which is more probable, and eventually it is a matured phenomena where it keeps changing season to season. It is not like a long term prediction. I cannot say what would I be experiencing next summer compared to this summer. So if I know, or if I have a data of say a person X has experienced the past 5 or 6 summers in this way, his thermal experience was this, I may not be able to say 100% surely that the next summer with this given temperature he is going to say comfortable or uncomfortable. Whereas the building versus environment response is more or less cyclic. Then comes how occupant interacts with the building. The interaction has 2 dimensions. One is more design oriented, how we use the space, what we do, move around. This comes more into the design side, but what we are talking about, more relevant to what we are talking about, is how we use the adaptive features provided in the building. As a designer, it bothers you in order to give proper adaptive mechanisms in the building, build in proper adaptive mechanism which will facilitate the occupant to improve his level of comfort rather than opting for mechanical systems. This is more of a probabilistic behavior. I can open the building, probably I will open, I can open the window, probably I may open the window, to what percentage people are willing to use it. So this is more of a probabilistic interaction. Occupant using the building rather more focused, using its adaptive features, then the comfort perception considerably changes. So these 3 things together, how harsh is the environment, say typically take a summer the building is behaving in some manner in summer, then the people are using the building in some way, they are closing the windows in the daytime, opening it in the night time for proper night ventilation. So, this totally determines the overall indoor thermal perception. This whole phenomena can be combined together and say what is the overall adaptive thermal comfort available for the person. We saw this particular comfort boundary in the last class. On a psychrometric chart, this ASHRAE model, they have superimposed a comfort zone for summer and winter, where they set this particular boundary, the area lying within this boundary, the temperature humidity combinations would provide comfort for a set of people. And we also saw moving towards the right or left how it affects being comfortable or uncomfortable. But to simplify this, the adaptive model gets you a comfort boundary something like this. What you have in x axis is the mean outdoor air temperature, this could be daily mean or this could be monthly mean. Here we have indoor operative temperature, and simply this particular band is said to be a comfort zone. I will give you the history of how this particular thing itself is developed, but before getting there you will see 4 lines here. The first two, the inner set, this makes this shaded portion, this says 90% acceptability limits. So, when the prevailing mean outdoor temperature is like this particular operative temperature set is said to be acceptable for 90% acceptability limit, then the next broader one is 80% acceptable by 80% of people. Another interesting thing that you need to notice here, the comfort boundary is not a straight line like you see in your conventional model. We always say 24.5 degree plus or minus 1.5 or 2 degrees is comfortable, but this particular model says that the indoor operative temperature or the comfort temperature, rather the comfort band, increases proportionally with respect to the prevailing outdoor air temperature. For example, what is comfortable to you at 10 degree ambient temperature is not comfortable to you at 30 degrees ambient temperature. When the prevailing mean temperature, for example the daily mean temperature is 20 degrees, then 10 degrees, then your probable indoor operative temperature comfort could be between 20 and 22, somewhere in this area. But then when the prevailing outdoor mean temperature gets higher, for example you are going towards summer somewhere between 30-32 degrees, then this particular limit, the same 20 to 22 degrees, you will perceive as being cool or cold, whereas you would prefer being in a temperature of something like 28 degrees where you would express comfort. Similarly, in winters the same 28 degree you will express it as being warm, probably not hot, but you would probably say that this is a warm condition rather than saying that it is comfortable. This particular graph has been developed as a part of what is referred as research project 884. This is one of the common or standard reference. There is a interesting report available, an exhaustive report. This particular report sequentially analyzed different components of thermal comfort. It took into consideration numerous field studies which were conducted. We will talk more about the procedures for field studies, but lot of field studies which are where people ask about thermal perception with different group of people performing the actual activities rather than a controlled laboratory setting. This is where there is a striking difference between the adaptive model and the standard thermal comfort model. As we said, for example the Fanger's comfort model or the tropical summer index model, the Indian model, these particular models were developed in controlled laboratory setting. Like you get some 100 people to the lab, you control the environment, indoor environment, you modify the temperature, radiation, humidity, air velocity, and for each of these modification you make them respond as to how they feel. But one major difference which happens from this comfort to what we actually experience is, in field we are not bound to this third party controlled temperature or any environmental settings. We are free to adapt to certain extent. Of course, to certain extent we also are bound to do certain things. Say if I am working in an office, I am bound to follow a dress code, I am bound to do or not do certain things, but still I have certain amount of flexibility to adapt myself to the thermal environment. So in this case people found there is a lot of difference between the laboratory controlled results of comfort versus the field results of comfort, thermal comfort. So, taking that into account as a central theme, this particular report looked at different field studies and evidence from field where there was a difference between the lab controlled comfort perception versus what actually people experience in the field. Putting all these data together, this database is also available online for you if somebody wants to explore. This is from different countries, prominently from Southeast Asian countries. If you are interested to take a relook at the data, derive something out of it, you can feel free, you can search for RP884. Lot of data, the whole set of data is sequentially stored and it is freely available for assessment. Taking those data, this particular analysis was made and this is a fit which was brought in, and people found that 90% acceptable limit lies somewhere here. We will look at few more example specific field studies and how these things are developed in the following things. How do we measure thermal adaptation? If we say measuring comfort, there are lot of indices. We also looked at few of them like Fanger's PMV, or for example the effective temperature or TSI. You basically assess the thermoregulatory phenomena. We saw the Pierce's 2-node model where you study the thermoregulation phenomena of the body itself. But when you say thermal adaptation, you are talking about a set of dynamic people, or people doing dynamic mechanisms to keep themselves comfortable. People are under movement, they are not idle. So primarily these adaptive studies revolve around conducting field measurements of comfort. It has two components, one is physical measurement accompanied by subjective assessment. It is like you have a set of sensors, you go to the field, you measure the condition, parallelly you also ask people how do they feel. So how do we ask how do they feel and what do you measure? This is what you are going to look at in this section. There are three important scales which we have to keep in mind in order to do thermal comfort studies on field. Today you find lot of studies, such studies are being reported. So if one is interested to conduct these studies, we need a lot of more studies for India specifically, because the climate is diverse, cultural variations are really huge, we have lot of socio psychological differences. So with these things we will need a lot of field evidence. If one is interested, you have to have in mind three important scale. The first is the Ashray scale. All these things are double Likert scale. This is a 7-point scale. You have 0 which is thermal neutrality in the center. Towards the right you have slightly cool, cool and cold, -1, -2 and -3. Here you have +1, +2, +3 representing slightly warm, warm and hot. This typically we call thermal sensation mode, but it depends, certain authors refer it as the actual sensation mode, ASV. There is a different terminology, but the scale remains the same. Ideally what you ask is what do you perceive. When you have to ask this question, you need to ask them what is your thermal perception or what is your thermal sensation right now. The next particular scale which is interesting is the Bedford scale. This looks alike in terms of the numbers, in terms of the balance. It is also a 7-point scale starting from 0, -3 in one side and +3 in the other side, but there is a small difference. In fact, it is a major difference when people answer for this, small difference in terms of the verbal variations which is put in here. 0 is neutral here, but when you go to -1 or +1, you find the term called comfortably cool or comfortably warm. We refer this commonly as a comfort scale rather than a simple sensation scale. This is like a thermal sensation scale. What do you sense the thermal environment like? But this is like, are you comfortable with it? I am going to show you some field evidences how the answers, the same person answering in these two scales, there is a lot of difference in the way he answers. This rather asks you whether you are comfortable. When you say I am feeling slightly cool, it means that the environment is slightly cool. When you say I am feeling comfortably cool, it is cool but you are comfortable with it. The next important scale is a 3-point scale which is McIntyre scale, commonly referred as McIntyre scale. This is very crucial information which you get from the field. It's just 3 simple things: I need cooler, I need warmer, or I can accept. For instance, a person might say I am feeling slightly warm, but he may say it is comfortably warm, and he can also say I can accept this, which means this particular set of thermal environment, if you go with the sensation scale, you may say that no, this is slightly warm, you need to bring it to neutrality, which means that people always do not need neutrality, but they can also be feeling comfortably warm. For example, a slightly increased temperature or a radiant heating will give you or will keep you comfortably warm in winter, and you can still accept that particular thermal condition. A sample comfort questionnaire, just to show you that there are a lot of dimensions in which you can assess thermal comfort. A standard like ASHRAE 55 thermal comfort standard would give you in the appendix what all basic questions you need to ask, how to ask and what to do. Basically these comfort questionnaires will have their date, time stamp plus age, gender, you will be noting it, but other than that you will also have some place where you will have to note the environmental criteria. What is the here we had room dimension and basic features of the room, about whether the windows are open, fan is on, off, what type of thermal environment is prevailing in the room, plus the design configuration. Apart from clothing and activity level, when I say activity level, it is not like the momentary activity the person is doing, you have to also record what activity this person was doing for the past 1 hour at least, so that you get a fair idea about what thermoregulation is happening in a particular person. Apart from this environmental criteria, you ask a set of questions. It can be short questionnaire, it can be a long questionnaire. This one I am showing you is a little exhaustive one. Apart from the basic 3 scales, you also can ask them about how do you feel about the air movement, whether it is breezy, whether it is windy, what about the sultriness, whether it is humid, sultry, or whether do you feel it like dry. You can also ask about the health conditions. As you ask more questions in a systematic way, the better information or inference can be made out of this. There are 2 types of surveys which are typically done. One is a transfer survey, which is called right here right now. You go with a questionnaire, go with a set of instruments, let the instrument settle down with its sensitivity, say it may take a minute to 5 minutes depending on the instrument sensitivity. Then you also let the person settle down, you explain him what you are trying to do, and then you ask the question saying it can be exhaustive, it may take about 5 minutes, he will be answering you about each of these questions and what he was doing for the past 1 hour, where he comes from, stuff like that, plus your measurements will be going on. Say 10 to 15 minutes of this interaction will give you a set of answers from a particular respondent. This is one type, right here right now, or a transfer survey. It is like a doorstep survey, you have to get in of course, but it is like knock the door, get in, do the survey. But other type of survey which is even more informative is a longitudinal survey, where you keep asking the same person a set of questions multiple times. Say it can be 3 or 4 times a day, 2 it can go all through the season, he may be answering it daily, he may be answering it 3 times daily over the year. As you have provision, the more stable and more informative the data is. But one small constraint is you cannot ask exhaustive questions again and again to the same person. The number of questions have to be limited, and the number of measurement parameters also might be might have to be limited, because if you have to install such a set of specific instrumentation for each person, it may be really a costly affair. Typical set of instrumentation, before we talk about instrumentation, there are 3 classes of survey. Level 3 surveys, for instance, there are 3 levels. Level 3 is like you have minimum instruments, you measure temperature, humidity, probably air velocity. Again sensitivity varies. I am giving you a very basic information about this. Say you have temperature, humidity and you are measuring air velocity, you also ask the person a few questions about the thermal environment. It does not cost you much, but still you manage to get some amount of data, but the accuracy of the data considerably varies. As you go to level 2 surveys, level 2 you need to measure at least 4 environmental parameters: temperature, humidity, air velocity, as well as radiation. In terms of globe temperature, you would have to measure, apart from noting down their activity and metabolic activity and the clothing insulation. Then comes level 1 survey, where the temperature, humidity as well as the thermal environments are recorded at 3 different levels. Say if a person is seated, you take in his foot level, the waist level as well as the head level, for same with the standing person. Apart from this, it also needs a continuous recording for at least a duration, so that you measure the thermal environment around him for a particular duration. It is not like a momentary survey. So, there are 3 levels. Of course, level 1 gives you more standard and stable information, but it is eventually it is costly. For example, these are, this is a very small device we used to have for measuring temperature, humidity as well as globe temperature, along with a hardware anemometer which measures air velocity. Hardware anemometer has better sensitivity for indoor measurements. This gives you much better result than Vane anemometer. This is a comfort meter which directly measures Fanger's predicted mean vote. I am not talking much in detail about the construction of this instrument, but later versions are available. This is a very useful instrument. It directly gives you +3 to -3 if you set metabolic activity and the clothing insulation. This is one of the very fine instruments which even it has been in use for the past 30 years, it is still being updated. Apart from this, if you have to do level 1 survey, you have to have at least 2 sets of instruments like this measuring in 2 different levels. You can measure temperature, humidity, air velocity, then the radiant asymmetry, globe temperature, air at least 2 different heights, plus you need a data logger which needs to continuously be recording at specific frequencies. I will show you few results so as to touch base on what we are actually talking about. We did a subjective evaluation or adaptive comfort survey for a set of people in a warm humid climatic condition. I am going to show you some results and relate to what we have been talking about. What we did a survey of about 300 plus, about 330 people were surveyed. There were short term surveys like transverse surveys, there were longitudinal surveys. The overall data set was something like 1500, around 1500 numbers data sets were there, because longitudinal about 100 people were answering again and again for specific duration during summer, during winter. So, the data set was about 1500. Measurements were taken. What you see here is the indoor globe temperature, and what you see here is a thermal sensation vote. This is the first in the 3 scale that I was talking about. This is the ASHRAE scale, thermal sensation. People were answering on how they actually sense the thermal environment. The temperatures recorded were something like 25 degrees all the way up to 40 degrees of indoor globe temperature. The measurements were taken, and this is the response given by people. There are 2-3 interesting things which we need to note. See, whenever you do adaptive comfort survey, this is what you will get. You will get a graph like this. When you plot, you will get a graph like this. What it means, say take a temperature of say 36 degree. You have set of points, dots across the y axis. It does not of course come down, which means this is cold, this is cool, this is cool, cold and very cold, this is on the hotter side. You do not get the colder responses during this particular temperature. Of course 36 degree nobody tells I am feeling cool, which means there is an anomaly in the measurement. But still what we found, there were a set of people who were also saying they were okay with it, that is they said it is thermally neutral. I will tell you who said those things. Then there are a set of people who are responding somewhere between 1 and 2, and there were a good amount of people responding between 2 and 3. You get more data of course on the higher side as the temperatures go up, whereas if you see temperature like 26 degree, you still have some people saying I am thermally neutral, but still you find more number of votes coming towards the colder side. As I said, this is like warm humid, more specifically it is a hot and humid region. This was recorded in Chennai, where winters are not that prominent. As it gets lesser than 25 degrees, people start saying that it is a cold condition. On contrary, if you go to a colder climate or a composite region, you are used to 25 degrees, 26 degrees, because your temperatures drop as low as 5-6 degrees. So 25 is comfortable. You may get further lower temperatures, you may get this response, you may not get this response. So one important thing we need to note, this particular dispersion is very location specific, very specific to the socio-cultural group which we are talking about. Coming back to this particular response, some people had responded that they were neutral, feeling neutral, they are okay with it. This actually corresponded to a set of people from different socio-cultural segments of the society. We recorded with a set of fishermen, for example, was one group of people from whom response was taken. Of course, it was an indoor measurement, not outdoor measurement. Fishermen's colony we covered. The other measurements were taken in HIG homes, like where people already are using minimum 2 air conditioners and their thermal responses. So, this is a total response, so you have a wider dispersion. Similar thing, yeah, one more important thing is when you fit a curve here, this particular line is a simple linear fit, it crosses 29 degrees at the thermal sensation mode of 0, which means the thermal neutrality for this total set of people is around 29 degree. If you take plus 0.5 and minus 0.5, say 90% acceptability, then the limit would be somewhere between 27.5 to 30.5. So, this would be the range which is thermally acceptable if you go with the thermal sensation vote. A similar assessment done with tropical summer index, because this is only temperature, globe temperature response. If you include humidity and air velocity, you can do the same thing with TSI. This is the third scale which I was talking about, the McIntyre scale. You ask them whether you can accept you need warmer or you need a cooler environment. You have tropical summer index here and percent of subjects here. This is a logit analysis. If you see this green line, this is like I can accept. As the temperature TSI increases, the can accept votes come down. The percentage of people saying I can accept comes down. Percentage of people saying I need cooler goes up, and need warmer naturally comes down. We did not go much on the colder side of the recording, so this particular line fit did not really come well, because most of it was taken in the warm. Nobody is going to say I need warmer. Had we been doing the surveys on the other side, say 0 to 25 degree, this line would fit much better. Taking this cue, if you see the need cooler and need warmer line meet, this particular thing is probably the thermal preference of people. Getting back to the previous slide, what actually they were saying, they were feeling thermoneutral about, they were saying I am feeling thermoneutral at 29 degrees, whereas when you ask them whether you can accept it or what do you prefer, it comes to around 27 degree, which says that 27 degree is a thermal preference, but they can sensation wise they are okay with 29 degrees. This 2 degree difference will probably induce people to adapt for more air conditioning system or getting into more cooler environments. There are also other parameters like microclimate, not getting much into the details of it, you have publications based on this you can refer to, but just to give you a simple example, taking two different housing colonies, this is like microclimate recording of that particular thing, temperature, humidity and the ambient noise level. Why I have put noise level is, one was in a major traffic intersection, people were not able to use their balconies or windows because it was too noisy, as well as air pollution was pretty high. The other one was in a quieter environment. Temperatures were also considerably different. This particular one, the maximum temperature during summer went up to 40, whereas here it was around 37, 38 on a similar day. These were taken from Met Department stations in these two locations, the same city. Humidity levels are also different. If you carefully assess, this particular thing is on the ASHRAE scale, this is a TSV on the ASHRAE scale. The responses are more or less same between these two housing colonies, whereas if you ask them on Bedford scale how comfortable you are, people located in this particular thing, the expression of comfort considerably changes. This is heat discomfort, so it is on the other side of it. Heat discomfort, the higher the number is, more people are saying I am feeling more heat discomfort. Say take a temperature like 31 degree, this particular thing is located in a quieter setting, people had the flexibility to use their windows, balconies, they can open windows, they can get more ventilation compared to these people who are bound to keep their windows, balconies closed. At same temperature, say temperature of 31 degrees, almost double the percentage of people said they were feeling uncomfortable or they were experiencing heat discomfort compared to this particular thing. This happened at almost all the temperatures. So, as a designer, what this means to you, microclimate or setting up the microclimate is very crucial, not just ambient pollution alone is a major thing, visual privacy especially in apartments. When you have two adjacent blocks looking at each other, people do not open the windows, it affects the ventilation, but it affects thermal adaptation in the context we are talking about, as a result of which people are going to express more heat discomfort, and this would lead to usage of more energy in terms of mechanical systems. Let us take a look at some adaptive comfort models. There are a lot of studies, and each study is reporting about a different set of more or less overlapping, but a different range of temperature, humidity condition or environmental condition with which people are able to adapt. One standard reference is the ASHRAE standard model, where comfort temperature or Tcomf can be expressed as 0.33 into TOM. OM is monthly outdoor mean temperature. For a particular month you take the outdoor mean temperature, 0.33 of it plus 17.8. This is a standard reference, but as you see there are lot of studies in India as well as Southeast Asia plus across the globe. There are more studies. This is not a total list of the whole thing, and each one of it more or less, if you see, it is like 0.3, 0.15 or close to 0.2 of globe temperature. Most of these studies I have collected were based on globe temperature, say plus or minus some variable, and the neutral temperature also we find that it is considerably different. For example, if you take the colder climate like Nepal, the neutral temperature was around 22 degrees. As a contrary, if you see a composite climate or a hot humid climate, you find neutral temperature as high as close to 30 degrees, 29 degrees precisely. So there are lot of more comfort models, but more or less they are like regression models developed based on field evidences. If you compare two cities in India, I have taken the standard comfort model, the ASHRAE model, and I have plotted two different cities based on the monthly mean temperature. So this particular thing is month here, this is outdoor air temperature. This thin line show the monthly maximum, mean maximum and mean minimum. The dots represent the mean maximum and mean minimum. Then the center one is the monthly mean, and the red line shows the Tcomf calculated based on this particular equation. So this is for Ahmedabad, where you find the comfort temperature varies somewhere from 24 degrees and it can go as high as 31 degrees during summer, whereas if you take a city like Bangalore, the comfort temperature is close to 25 degrees during winter and it can go up to say around 28 degrees during summer. There is not much of a difference. Keeping this in mind, Fanger revised his comfort model, or rather proposed the addition and add on to his own comfort model, the PMV PPD model. He introduced a factor called expectancy factor, which is nothing but to scale down the actual prediction of the PMV. For example, if your PMV is 2, which means you are feeling hot, then he says that in region where AC buildings are common, you can retain that particular vote by itself, it can be just 2, whereas if there is a region where there are very few AC buildings, or you take a socio-economic strata where people are not able to afford for more air conditioners, then he is saying that the PMV value can be scaled down as low as 0.5, that is half of it. Instead of being hot, it would be warm. So the same model he is saying it can be extended using this. We did try to compare the actual predicted model, the same graph I showed you, with the PMV's prediction. Always the standard PMV model tends to over predict. If it is like neutral, it says it is really warm and it goes up high, but introducing a weightage of around 0.6, it comes closer, but it cannot directly align. Of course, this particular trend line changes from location to location, but more or less around 0.5 to 0.6 in Indian condition, the PMV comes much closer to the predicted, or sorry, the actual perceived thermal comfort. One of the recent addition to the model, not so recent but about 6 to 8 years back, this was implemented in the European codes as well. Here this is the concept of running mean outdoor temperature. Instead of taking daily mean or monthly mean temperature, monthly mean outdoor temperature, the concept of using running mean temperature, like it's a short term thermal history that you are accounting for. Take the mean temperature of the past 7 days and then like you do a decay calculation, kind of you give more weightage for yesterday's mean temperature, slightly lesser weightage for previous day, and it goes on for the past 7 or 8 days. It can go longer as well, but typically 5 to 7 days is taken. Then instead of a particular daily mean, you get something called running mean temperature, and comfort temperature typically correlates much better with the running mean temperature rather than the actual ambient mean. We have also verified the same thing, it has a better coincidence with the running mean temperature as compared to the actual daily mean temperature or monthly mean temperature. This is a thing, this is like typical outdoor air temperature, mean temperature of a particular day versus this is a running mean outdoor temperature. The correlations were much closer, you had a better m value plus the r square values are also slightly higher here. Similarly, this is how the band, the comfort band, using the previous equation I showed you, this is for Ahmedabad, the light blue line represents the actual hourly temperature variation, the blue one is a mean daily mean temperature, the red one is a running mean temperature. This band here tells you what is a adaptive boundary based on the running mean temperature. So, it continuously varies all through the year, it goes up to around 33 degrees maximum and as low as around 22-23 degrees during winter, and this is the case of Bangalore. The boundary more or less lies similar, but the fluctuations and the spread is different. Why do you have to know all this? We will talk more about this particular graph elaborately in further modules, but this particular thermal adaptation has a significant impact on the actual monthly energy consumption of a building. We will talk about energy efficiency, in those modules we will touch upon these things, but to connect these two modules, one of the studies which we found, which we did, we found that there is a considerable amount of difference for the same user group. People are similar, the houses they live in are similar, orientation, floor configuration, design configurations are all similar, but due to personal variables and adaptive phenomena which they are getting into, there is a considerable difference between their monthly energy consumption. Monthly bills seem to be quite different from each other. We will stop this particular module here. We looked at the psychological and physio-psychological dimensions of thermal comfort, then we talked about thermal adaptation and major factors influencing it. We looked at how to conduct an adaptive comfort survey and how do you measure these parameters in field, and we also looked at few adaptive comfort models in this way. Thank you.